Good evening, friends. Good evening, friends. Today is third day for our town planning and building overseas examination preparation through ACE online presentations. I wish to take some extra time because we are unable to cover questions as far as possible. We will take up to 8:30. So last class we had some discussion on dimensioning, lot of discussion in fact on dimensioning. Then construction of geometric figures. Of course we had a lot of discussion with the polygons. In this class, we will continue the geometric constructions and cover some part of orthographic projections and then some introduction to scales, and we will try questions, answers from whole papers, multiple choice questions we will try today, right? So, as this again I am showing you, almost this is over. Now we are covering from these areas. Okay. Yesterday we had a lot of discussion on this, and I have also prepared the PDF for you in which the answers for these are available. Just I am showing to you, and this sketch also I have added to let you know what is a haunch and what is a segment in general. But our haunch here is this haunch actually. So that radius is different, and of course just for a better understanding only I have provided that, okay? Right. And here you have to also understand the terminology. For example, inscribed and circumscribed are very relative terms. This is one thing which I want to tell you. Very relative terms. If I speak about this case here, now just I am showing you the methods of drawing different polygons, which of course they are available. All of you know them. Just for a revision only I am just showing them. My point is, see, by angles method, this is how you can draw by putting angles and all, a pentagon, right? How we know 108 degrees? Because we have that formula, no? Interior angle formula. From that we know that, right? And another method, this is the general method. You may have some questions on general method. What is the general method? So you can here see, for general method what we do is, if you want to construct a polygon with a given, sorry I have not taken that, okay. If you want to construct a polygon with some given side, say x, the process is, by general method we construct a triangle, right angle triangle, and then draw 60 degrees lines and 45 degrees line and bisect this triangle. This is how you can see. We construct a 90 degrees line first, and see, suppose on this I am explaining you, this is the length of the side on which you have to draw a pentagon by general method. A length is 6 centimeters. What we do is, first we draw a light line and then mark this AB with a divider taking from the scale. We mark that distance, okay? Mark A and B. Then from this point A, we draw 45 degrees line and 60 degrees line, and we also develop a midpoint perpendicular, or you bisect this line AB so that you get a midpoint perpendicular. Now this midpoint perpendicular of line AB is intersected by 45 degrees line here, 60 degrees line here, okay. Therefore, you mark them as 4 and 6 and you bisect this distance of 4 and 6 like this, you know how to bisect the line, you know that, right? And then you get the point 5, midpoint. I said this as 4 and this as 6, therefore I call this as 5. Why I call this 4, why I call this 6 in the concession, if you know, you understand that quickly. For example, why I call this 4? This 4 is through 45 degrees line. So, if I take a circle with center as 4 and the radius as the distance from A to 4 and draw the circle, within that circle, you can develop a square. Similarly, for 6, within that you can develop a general method, all you have done, just I am refreshing for you, right? You can develop a hexagon, because if I draw a circle through A and B with the center as 4, within that I am getting square. Same through A and B, if I draw a circle with center as 6 and radius as 6 to A, within that I will be able to draw the hexagon. Therefore, with the center as 5 and A to 5 as the radius, if I draw the circle, then within that circle, definitely like this, I will get the pentagon. How? Just after drawing the circle, for example, this is the case of a circle with center as 5 and radius as what? Radius as 5 to A. 5 to A as the radius. With that, after drawing the circle, you just take the distance AB, and with that, you go on cutting arcs on the circle and you will get this required pentagon. So, this is why this is called general method, because with this method you can construct any number of polygons starting from a square, okay. Now you can see another method of drawing the pentagon. I have named the points such that you can understand how to get this, okay. So, because you are all experienced people, these sketches were drawn as like self-explanatory. Please go through them. So, questions may be like that. To draw a hexagon, to draw an octagon, see this is an octagon, okay. To draw an octagon, the number of sides here is 8. What set square we use? That may be a question. Is it 30 or 60 or 45 or 90? See, any set square will have a 90 degrees, right? But what are the two set squares we use? 30 or 60 set square we call one, and another is 45 degree set square. So, you use this 30 or 60 degree set square for hexagon, whereas this for octagon. You may have a question on that. There may be some confusingly written hexagon and octagon together. They will give you in the options number of combinations by jumbling things. So, if you have a perfect understanding, you can comfortably answer this, okay. Okay. So, that is why for an octagon we require what? A 45 degree set square. For a hexagon we require 30 degree set square. These are the polygons which you can build with only set square, scale and pencil, okay. Of course, you have to need, for marking distances, you may need a divider or a compass to cut the arcs. So, there is one method, hexagon being, no, it's a combination of 6 equilateral triangles. There are several methods of drawing hexagons. So, like this also, by method of arcs we can also do that. How we get this thing? How we get that? With the same, because we know the hexagon inside triangle for each side is a 60 degree triangle, right? You can, after drawing AB, build up a 60 degrees triangle, get the center, with that corner distance, that is center O to A distance, you draw the circle, and on that go on marking that. Okay, and similarly here I have shown you a heptagon, that is 7-sided figure. By general method, you can see, expand and see how these lines are there, how the point 5 is obtained by bisecting this central mid perpendicular, and in an expanded fashion I have shown those points, and this is the proof how the general method is developed. For example, as I told you, with the point 4 as center, if you draw the circle, then on that circle you get the square. With the center 6, you get the hexagon. Therefore, the bisector of 6 and 4 will give you a point here on this mid perpendicular of AB, and with that 5, you can draw the circle and develop the pentagon. If you want any number like that, you go on repeating this distance here, 6, 7, 8, 9, like that. So that's why, because of this method, we can draw any polygon starting from the square. So it's called general method, okay. So this is how it is explained, okay. The principle behind the general method is shown to you here, okay. Now, this is what I was telling you, what is the meaning of circumscribing and inscribing. It's a very relative terms. Suppose, here what we did, we have circumscribed. Here question is circumscribe a hexagon on a circle of radius 40 mm. That is, how do you do that? For that you may have a question like that. What is asked? You have to circumscribe a hexagon on a circle of given radius. So first what you draw, that may be question. For that you should have an understanding that I have to draw the circle, on that I have to develop the hexagon like this. No. Like this. Okay. Okay. So for this I should have that idea that first I should draw the circle and develop a hexagon on that. Like that you should have the idea first. So forget about this. If a sketch is given like this, how relatively you can say? If you want to describe the circle, you can say, forget about which is done and all. Some figure is given like this to you. Then what you can say about this figure with respect to the two words like circumscribing and inscribing, okay. This circle, if I say, it is inscribed in a hexagon, isn't it so? Or if they consider the hexagon, it is circumscribed over a circle, okay. So if you use that inscribe, you call it in. If you use the word circumscribe, you use the word what? About or on. About or on, like that, okay. So like that you can see there may be questions involving two sets and describing them. So you should have pakka command over the wording, use of the wording circumscribe and inscribe, okay. Okay. So these are the things, and of course regarding other figures like the geometry, you have all fundamentals. Many of you have crossed that level. So I did not cover things like construction of triangles, etc. So any reference you can take and go with that, because lot we have to cover that, okay. So we have covered regular way of drawing polygons, okay. And this is very important in the examination point of view. If the geometric figures, in that if he has considered the properties of the hexagon or any polygon, you can do that, okay. So while explaining to you yesterday, I went to a little bit faster, so you can do yourself and check all these things and know the background of all these things, okay. So okay, fine, we will take up the projections, orthographic projections, okay. So what is a projection? First of all, projection in our drawing, in the sense of our engineering drawing, the projection is the way of visualizing a picture and drawing its image, okay. So and there are different methods of projection. So we can see a classification. This is a common, because all sketches are in one place. I have just taken it from Wikipedia. You can see the classification of orthometric, orthographic projections as a part of a graphical projections, in which orthographic projections, oblique views and axonometric views, they will come under parallel projections. I will tell why parallel projection. And the other set is, say, perspective projection. The architects know this better, okay, about the perspectives views, okay. And in the orthographic projections, we have the chance of representing only 2 dimensions. So they are multi-views projections to represent the objects. 2-dimensional views are sketches, because each sketch, the dimensions or the shapes will be in each view will have either length and height, or length and breadth, or breadth and height, like that, okay. So this, while doing things, you understand this. Principles of orthographic projections, okay. First of all, what are these orthographic projections, okay? You can see from this, ortho means perpendicular, and for drawing these things, we use certain tools like a picture plane. We visualize them using rays of light called projectors. Then for the purpose of understanding the principle, we use an observer and an object and a picture plane. So to draw these things, we require things like a projector. That is, projector is not which projects, the process is same. It's a line, ray of light, you call it a projector, okay. And then picture plane, okay. And then observer, and then the object, okay. Why they are called orthographic projections are, here the projectors are perpendicular to each other, planes are perpendicular to each other, the projectors intersect the plane in a perpendicular manner. Because of that, they are called so. And this is a graphic projection or geometric way of drawing figures with mathematical compatibility. So this is where from the difference comes starting, difference starts coming between the artistic drawings and engineering drawing. Here we have graphic projection, in which we have orthographic projections, a class. So in graphic projections, this is a geometric way of drawing figures with mathematical compatibility. May I have a question on that? What kind of compatibility we have? A mathematical compatibility. That means with them, we can see how the things will match perfectly. As per scale, we get them perfectly. And then It's an engineering approach in the drawing, okay, most suitable for working drawing. So what is the use of orthographic positions? It's the best way to represent the figures, okay, so that in the production or for the building, see, for buildings what we do? We draw the plan and then elevation and the cross section. What are these things? Plan, elevation, cross section. They are nothing but orthographic projections of the building which you visualize and draw, so that in the site from these plans and cross sections they will construct the building. So here we will see the fundamentals. Now, as I told you, we use these terms like projector, okay, planes, etc. for understanding the orthographic projections. One example is given here, wherein we take an object like this, like say, what is this object? This object is what? It's a frustum of a cone, okay? A frustum of a cone with the base diameter more here, okay? So you just imagine there are two planes, a horizontal plane here. So this is what? Horizontal plane, okay? And this is vertical plane. And both are intersecting at this point. So the intersection of two planes, in the drawing we represent it by ground line or XY line, okay? XY line, okay? So horizontal plane, vertical plane, we use these terms very frequently to describe the positions of the objects. So how to visualize the objects and how to draw the figures. Now here the problem is this. From here onwards we should be able to visualize an object and draw the figures. To visualize the object and draw the figure, when the object is a three-dimensional object, this object is a three-dimensional object, but your drawing is only a two-dimensional drawing, is it not so? Therefore, instead of having three dimensions in the orthographic projections, in each side, if you see, from different sides you see, such that from each side at least you get two dimensions, that's all. From each side at least we get two dimensions. That is the requirement. To draw such figures, we need to visualize two planes, like a horizontal plane and a vertical plane. What are horizontal? You know all that, no? This floor of this room is a horizontal plane. The walls are vertical planes, okay? Like that. Now here, as I told you, we first, for the understanding purpose, take a cone and keep it. When you take two planes like that, you know, we form four quadrants. How these four quadrants are formed? The entire space region is first divided into something above the horizontal plane and below the horizontal plane. Is it not so? Entire space. Suppose if I just keep a plane here, the entire space can be described as something above the plane and below the plane, right? Similarly, keeping this plane like that only, if I place another plane like this, and this the plane, the region above the plane, that is above HP, is again divided into left of this and right of this, and below also is divided like this. So totally when you place two planes, we get in the entire space four regions. These four regions are called four quadrants. Quadrant means 1/4, okay? Four quadrants. How we represent those quadrants? The standard way of representing them is, if you see from this side, these four planes will appear like this. This is HP, this is vertical plane, okay? Vertical plane. So this above HP, you start from here, 1, 2, 3, 4. So those four are four quadrants, okay? So What is first and second quadrants? They are above HP. Third and fourth quadrants, they are below HP. Similarly, what are the quadrants left of vertical plane? 2 and 3, and the quadrants right of vertical plane 1 and 4. So we can place the object in any of the 4 quadrants so that we take the projections and draw the figures. For example, here we take it in this first quadrant, and for facilitating drawing a 2-dimensional figures, we view from one side and take the projection on the plane from the other side. For example, for this object, if I see from the top, its projection is traced on this plane. For this object, if I view from the front, I take its projection on this side. So we give names also. Always the first thing with respect to which we speak are the first front views. So this is front view, because the view obtained by taking a projection of this. See, you imagine that you are seeing like this, then its shade appears like this. Is it not so? Because you take the projectors connecting this object and this thing. So like this. Similarly, if you see from the top, we see the shades here. So we call it a plan. But here my drawing sheet is plane figure, whereas the shades that I am visualizing are in 3 dimension. For this purpose, to bring them in a single plane figure, we take we make this a turn like this. We turn this plane like this and then represent things. Similarly, if you turn like this, what happens is this front view will be appearing at the top. Front view will be, for this figure, front view will be appearing at the top like this, and top view will be appearing like this at the bottom. In between we have XY line. We have XY line. Anyway, details we will see further, because here we are only getting an introduction. Okay. So this you call front view, and this you call top view. See, for this it is a first angle projection, because we placed it in the first angle projection. How we got this is for what I said. We have to use terms like picture planes, observer, object, projectors. Without these 4, you don't have any chance of visualizing and drawing these things. What are those things? These are picture planes. So 4 things: picture plane, okay, or start from the observer, because it is we who do. So observer, we are drawing for a object, therefore observer first, next object next, and then we connect, we visualize that, so projector. And then the figure we take on a plane called a vertical plane or horizontal plane called a picture plane. How many picture planes? 2. Fundamentally only 2 picture planes. For other views like auxiliary views, etc., we take a different auxiliary planes. So that's a different issue. Fundamentally only there are 2 picture planes. So this is how we get it. After getting that, we turn it, and then we get the top view here, bottom view. Similarly, if you place the object here, then you draw the projection. Observer will be here only. In the previous case, as I said, you see from this side. That means observer is here. Picture plane is here. Object is in between observer and picture plane. You take a shadow on that. Okay. That is the first angle projection. So, whereas in the third angle projection, we take a shadow towards us from the object. For that, we need a transparent vertical plane. Transparent vertical plane or transparent plane. Same thing for the horizontal plane. Later on, you will get it. Similarly, so for this, to draw the figures, to draw the drawing of the, this view of this particular object, again observer is here, you take the shadow like this. Okay, so these are the projectors like this. We take the shadow here, and observer is here. So for the other view from the top side, here also, we have seen first from the front side and then from the top side. Here also, first time from the front side and next from the top. So we get a figure like this. Then this also again, as you know, the procedure is turning the horizontal plane in a clockwise manner to get these two figures one above the other. For that purpose, we just turn it and draw. This is the basic procedure. We'll discuss in detail later on. But one thing you have to understand here is there are only two quadrants in which we place the objects and observe. And we don't place the objects in the other quadrants. That is, what are the quadrants in which we place and observe the drawings? First quadrant, third quadrant. We will not use fourth quadrant or second quadrant just for the purpose of academic understandings. Points are given, sometimes maybe lines, but in practical we don't do that. So accordingly, if you have drawn the figures considering the object in the first quadrant, that kind of projection is called first angle projection. In orthographic projections, you will have either a first angle projection or third angle projection. So this in detail we will see that. So for this you get first angle projection. If you put the object here, you get a third angle projection. No chance of drawing second and fourth angles. Because there are two ways of showing, we should also have a convention for representing them, and these are the symbols. So while doing, we will discuss again. So just for understanding purpose, you can see how the views are drawn in the plane. See, this is an object. You see, what is this object? You have to also understand, when there is an object, what is the shape of the object. Okay. Then this is a slant surface and a front vertical surface, and this is a front vertical surface, and this is a top horizontal surface. Connecting these two, we have a cut here and this here. This object, when you see from this side, what are the surfaces you can observe? See, when you are seeing from this side, you will see this point, this surface we will see. Is it not so? See, you observe this, this you may not be able to visualize that because yesterday I have seen that. Okay, we'll only black will use. Okay. So you will see this surface, you see this surface, you see this surface, you see this surface. Is it not so? How many surfaces we can see? Because we are seeing this way. For example, you are seeing at me like this. You can see only front side. You cannot see these sides. Is it not so? You can't see my top. If you want to see my top, you have to go there and see down. Like that. So, like this, if you see, we can only see. How many surfaces we are able to see? 4 surfaces. Now you see, this surface is shown here. This surface is shown here. See, its length is more, but in a slant manner. Therefore, it appears less width. No? Similarly, this rectangle as it appears, and this because they are parallel to the projectors, we cannot see. So this may be a question. What are the surfaces which you cannot see in a view? Any surface which is parallel to the projector, you cannot see. Any surface which is inclined at some angle other than 0 to the plane and on the front side can see. See, you can see these two are perpendicular to the projector. When you are seeing, see, these are the projectors, okay. The projectors run from the observer through the object onto the picture plane in the first angle projection. The observer is, suppose you can also have that dot. When I am seeing this pen, my rays of light go like this in a divergent fashion. But for the orthographic projections, the assumption is the observer stands at a we take only parallel projection. That means we assume the observer at an infinite distance. Okay. At an infinite distance, when you see, the lines are parallel and they are perpendicular to the plane. Similar manner, you can also take the top view, seeing from the top view. Okay. If you from the top, then what are the surfaces you can see? Yes, this anyway you can see. This you can see. Only this you can see. So you can see those things and draw the figure, and you turn this so that for this in the first angle projection you get the front view like this and a top view as it is here, something like this. And in between it is standing on HP, so we have XY line here. The edge it is not working. So how we are able to draw on a sheet when it is in 2 dimensions only by turning this like this. Therefore, for the first angle projection, first thing front view, because the top view is drawn here and it is turned like this, it comes to the bottom. So in the first angle projection, the top view or plan comes below the XY line, front view above the XY line. But if you consider the third angle projection, you can see same object, so you can see the observer is here. So you need a transparent plane in the third angle projection. So you take the projection towards you. See, the projectors are coming like this. They are incidenting perpendicularly onto the plane. Then you see it's a figure like that, the front view. With respect to the front view, how is the top view? Because when you are using these planes and you have to turn like this top view, you turn like this, so it goes to top. So in the third angle projection, for the XY line, top view, you can see, top view will be at the top and front view will be at the bottom. You see the reverse? Okay. This is for the third angle projection. And they are indicated by the symbols, when we will understand it once again. So for that purpose, I am not explaining this to you. This is how we study the projection of the points. Okay. We have to, in the syllabus, we have to draw the projections of points, lines, planes and solid surfaces. Okay. This I am giving you because people during the practice, for the solids you can easily draw. Whereas for the points and lines it takes some time for visualization because smaller objects. So this I am just giving you with some 3-dimensional grids. Try to draw views for them, and the positions of the points are described here for you. Okay. And where they are in all the 4 quadrants. As I told you, we have only first and third angle projections. Just for understanding purpose, that's why I kept it here. Fourth and second, we don't have it. Just for the academic or examination purpose, we may have them. Okay. Right. We'll discuss. Of course, here, as I told you, we have to deal with points, lines, planes and solids. So what are these things? You can, sometimes you may have, based on the syllabus, certain things are there. You may be asked, what is a point? A point is a dimensionless entity, an item. Entity means an item. Entity means what? An item or an object. Okay. It has what property? If it is a length, if it is a line, we say length. If it is a point, what do you say? You can't say length, you can't say area, you can't say volume. But what you can say? Its location you can say. So the point is having only location property. This may be an objective question. Try to understand this concept. Okay. So only location property is for the point. When a point has a location property, others will also have. But the point, except the location property, it does not have any properties like length, etc., maybe you will name it. That is common even for line and okay. So it's a location and line. Line is a one-dimensional object. Yes, line is a one-dimensional object. A line connects 2 points. The shortest distance between 2 points is that length of the line. So line will have an end here, A, some end here, B, or a PQ, something like that. And then a plane. Plane is a two-dimensional object. It will have some length, it will have some height. Only 2 dimensions. Okay. So you take any number of points on the plane. Any number of points you take on the plane, you can draw lines through those points. But if there is a point which is not on the plane, then if you want to just test, take any 2 points on the plane, you can draw lines through any number of points, considering at least 2 points. If you want to draw a line, those 2 points should be on the plane. Whereas if you want to draw a line between 3 points, those 3 also should be on the plane. If one of the points is above or below the plane, you cannot draw a line. Okay, connecting these 3 points. So there will be questions like that. So understand the physical concept, you can answer any question. And then the solid. Solid is a 3-dimensional object. You can see this is what a triangular prism, a square prism, a hexagonal prism. These are what? Solids. Solids will have length, breadth, height, or depth. If it is something above ground level, you call it height. If it is below ground level, you call it depth. That's a common terminology. Similarly, length means in the x direction. In the plan, we use terms like length and width, like that. In the elevation, we use the terms length and height, like that. So length, breadth, height, all these are the directional terms. And this is how you can see the 4 quadrants: first quadrant, second quadrant, third quadrant, fourth quadrant. Okay, this is the scheme you have to understand. What are the angles in the coordinate geometry? If you measure the angle from this in an anti-clockwise direction, first quadrant is from 0 to 90, second quadrant is from 90 to 180, third is from 180 to 270, and fourth is from 270 to 360. May I have questions on that? And these are the main differences. See, more than the skill, those who are very comfortable with biotic things like this will be useful, especially when you don't have time for preparation. If you have practice, you don't need this. If you have practiced well, you don't need this. So I have just enlisted. This is from our ASC Engineering Services material. The object, the differences between the first angle and third angle projections. Okay, the object lies in the first quadrant. That's what we said. Whereas in the third angle, it lies in the third quadrant. Isn't it so? First angle, first quadrant, right? The object lies between the observer and the plane of projection, and the plane of projection is always behind the object. Is it not so? When you are drawing the first angle projection, the observer will be staying here and observing the object and seeing like this. So the object is in between the observer and the picture plane. Because you want to observe in the front direction like this, you are here. So it is the picture plane is here, observer is here, object is here. So object is between observer and picture plane. And if you want front view, you take like this. If you want the top view, again you have to observe from here. There also again observer here, object here, picture plane there. So there also object is in between observer and the picture plane. Okay. Whereas in the third quadrant, if you place the object here, again observer will be here only. You are seeing like that. You take the projection towards you. Therefore, here you need a transparent plane here. You see the object through the plane. Through the plane you see the object. So the plane is in between the object and the observer. See, The plane is in between the object and observer. Similarly, for the top view also, if you want to see this, you have to see from the top, no? So observer will be here. So again, there also observer, plane, object. So again, the picture plane is in between the observer and the object. Again, there you need a transparent screen. That's what it is written here. The plane of projection is assumed to be non-transparent, where in the first angle projection, because you take the shade on this, that means you have to draw on this. Okay, so that it requires something like a board. It's a non-transparent. This could be a question. Okay, in the non-transparent. Okay, please see, non is here. Don't. Okay, so the plane of projection is assumed to be non-transparent in the case of first angle projection, whereas the plane of projection is assumed to be a transparent plane in the case of third angle. That's what I said, no? Unless this is transparent in the third angle, the object is in third angle. Okay, so how can you see this? Unless this plane is transparent. Similarly, unless this plane is transparent, how can you see that? So that is the idea. Okay, and then the top view or plan view is always below the front view, or this is what you have seen, no, at the while drawing the plans, no, civil engineers always draw the first angle projection. So what we draw on the line, you draw the elevation at the top, plan at the bottom. That is first angle projection. Whereas in the third angle projection, with reference to the front view only we speak about the plan. In the first angle projection, take the front view. Where is the plan? First angle projection, plan is below the front view. Similarly, take the third angle projection. Where is the plan? With respect to the front view, top view is in the top. That is on the plan is in the top. Oh, okay. So top view top is third angle. Top view below front view first angle. That's all. Simple. Always. Always. Top view below the front view first angle. Top view top third angle. Okay. Like that you have to. Similarly, the side views will be, see, whatever side views, if you draw on that side of the elevation, that is first angle. That is third angle. If you see from one side and draw it on the opposite side, for example, third angle, what we said, with respect to the, right from the first angle we will discuss. In the case of first angle, with respect to the front view, when you see the top view, that will be drawn in the bottom, opposite side, front view. You view from the top, draw at the bottom in the first angle projection. Similarly, if you view from the right, you draw the right side view on the left side. If you view from the left side, you draw the left side view on the right side of the elevation, like that. Anyway, while drawing things, you will understand better. With a single sketch, we will discuss all these things. So, same direction lo vestindi third angle avutundi, opposite side lo vestindi first angle avutundi, atla annamata. Okay. And these are the symbols, and in your code you can see in your code it is written that recommended projections as per, in your syllabus it is written recommended projections as per the standards. This is the standard. PAS has recommended the use of first angle projection in line with the specifications of Indian Standards Organization adopted by all countries in the world. So, I don't know why that specific in the syllabus it is given. This is the answer for that. What is the recommended projection? First angle only. That's all. Why again? Because throughout the world people are following that. That's all. Okay. Even for civil engineers, right from the beginning we are only following the first angle projection. Okay. And these are the symbols. You can see here one example. In the first angle, if you see for the object like this, no? This is the object, okay? When you see from this side, you draw on this side. That's why first angle. When you see from this side, you see this circle full, but this circle you can't see full, therefore you have a dotted line here. So that is first angle. That is with reference to the front view. If I consider this front view like this front view is a trapezium like this, okay? With reference to the front view, how can you get a dotted line if you see from this side, you can't see this. Therefore, This means you are seeing from this side. That means with reference to the front view, you are seeing from the right hand side, you are drawing the view on the left hand side. Opposite, that's what I was telling you, right? Similarly, for this, with reference to the front view, this is 1 minute, third angle projection. This I have to place here, in fact. Okay, yeah, this I have to place here anyway. So if you see from this side, same side I have to draw here. In the last moment when I was editing, it was a mistake. Okay, so if you see from this side, here only we will get, it's not this. Okay, while giving you PDF, I will rectify that. Okay, so these are the main differences. Okay, you can understand this. You need not by heart this. You understand this. We will see that. Okay, so we will come back after 5 minutes. Okay, welcome back. We'll have another 1 hour session wherein we'll cover scales topic and some questions. Scales topic we may not be able to cover completely, we'll try, but we'll give time today for the questions. Okay. Now, what is a scale and what is its purpose in the engineering drawing? A scale, what is a scale? Scale is to measure, okay. He has scaled the height, we say, is it not so? That means he has gone through all that, like that, okay. A scale is an instrument to measure certain quantity. Weighing scale is there, it measures what? Weight, is it not so? Okay. So, in our context, it is the length measuring instrument, okay. Right. Why we need scale, first of all? Why should we discuss about scale? You can see the requirements of our drawing are, it should be drawn to a scale. There should be dimensional concurrence. If I draw the figure of this particular rectangle, in my sketch also, the ratio between the length and height should be same as the length and height of this particular board, like that, okay. So, that is dimensional concurrence. Then the technical feasibility. Suppose if you want to draw a very big, say, figure, technically you can't draw it to the true size, no? You have to draw it to a drawing sheet compatible size. For that we need a scale, okay. Then the detailing needs. Sometimes we may not use only one scale. The main building is drawn to say 1:50 scale. Some truss joint is drawn to 1:10 scale. So there you require different type of scales. Similarly, for accurate measurements, we may have to draw different type of scales like a diagonal scale, like that, okay. Accordingly, different scales have come into picture. So here we will see first what is a scale. Scale is a length measuring instrument in this context for engineering drawing. And then what is the need? These are the needs we said. And then the types, that is classification of scales, okay. So what are the classification? See, you can see plane scale. All of us, what is the first scale used by us? It's a simple 6 inches, no? A small scale, right? Metal or wooden only generally. In the lower classes, of course, plastic one otherwise, okay. Then we use a foot scale, we used a foot scale also, okay. So that scale is a plane scale. So it can measure only up to 2 decimal places, okay. Here you can see the normal scale, okay. How much you can say? Suppose if I want to measure, say 6.3 centimeters, okay. 6 plus 0.3, okay. 6.3 up to this, is it not so? So we are able to measure up to what? 1 decimal place only, 6.3, only 1 decimal place. Can I measure 6.32 or 35? Approximately I can mark 35, but it is not exactly. So for the third digit, we need another scale, that is the diagonal scale. We will see that. Okay. So plane scale can measure up to 1 or 2 decimal places only, okay. So if it is a lengthy one, you can say 2 like that, okay. And then diagonals to measure the lengths up to 2nd or 3rd decimal place, okay. 2nd or 3rd decimal place, right. So that is the purpose of the diagonal scale. And the vernier scale. Vernier scale, in fact, it is not a simple single piece. It requires 2 pieces, one a movable piece and another a single. In the theodolite you have seen that, or in the vernier calipers you have seen that. There will be 2 pieces. That is not feasible unless you make templates. There is no need also. in the drawing sheets. So vernier scale is only practical purpose. Okay. In fact, it's used for plumbing, etc., or in the workshop for a perfect measurement. We use a vernier calipers. Then only we need that. So in fact, it's not contextually used in civil engineering case. And then the comparative or corresponding scale. That is whatever scales we have been so far using, they are comparative scales. Scale on is like a simple strip, because it has two edges. Even for tape also, you see, one side you see centimeters, other side you see inches, right? Similarly for this example, when two are there, if it's only one there, it's a plane scale. It's also plane scale, comparative scale. On the other side you have other set of units. Here in the top you have centimeters, at the bottom you have inches. Is it not so for this? So if there are two like that, different units or different proportions, okay, that RF, etc., then you will understand that. You know the scale set, now I don't know nowadays anybody is using that. We used to have it, cardboard scale sets, M1, M2, etc., okay. There may be two like this, no? On one side you have one RF, on the other side you have another RF, okay, like that. And then if it is 2 units, same RF will be there. Otherwise, like that. Okay. If it is for only 1 unit, then you have different RF in the comparative scale. That's all. Then scale of chords. This is used to construct angular quantities in the absence of an angle measuring instrument. This is also obsolete. Nobody is using, to my knowledge. Nowadays we have laser instruments, even electronic instruments like total station. So many accurate ways of locating things are now available. Even the structural demands are also so big that you can't use the previous this thing. In any remote place, some requirement, if you understand the fundamentals, even without anything you can do certain things. With a simple tools you can measure quantities of angles and set out angles with 1 or 2 linear instruments. To know that concept only, this is still prevailing in our discussion. So scale of chords is used to what? To set angles. To set angles, we use that in the absence of an angle measuring instrument. And then the isometric use. We have seen in the orthographic projections, only in each view you have a length and width or length and height, like that, or width and height. Whereas in the 3-dimensional object, if you want to visualize, we need pictorial views. We have seen previously the oblique view, perspective view, like that, isometric view. From the 3 sides you can observe that. So for such things we need an isometric scale. Okay, here you can see an isometric scale. It is obtained in a particular fashion by drawing. When we discuss in detail, we will go to that, how to construct an isometric scale. We just take a horizontal line, then draw a 45 degrees line and draw a 30 degrees line. You take our true scale on this 45 degrees line, and from these graduations we draw verticals down to the 30 degrees line. In that case, this 45 degrees line represents the true length and the 30 degrees line represents the isometric length, which is around 82% of the true length. So these are the questions, etc. We will get that in detail. We will go through later on. You can see now plane and diagonal scales. So how do you construct the scale? You require certain fundamental knowledge about these scales. That is RF, representative fraction. What is RF? RF is a ratio. Ratio means something by other thing. Okay? What is that? When you want to draw the sketch of an object on a drawing sheet, if the object size is compatible with the drawing sheet to the actual measurements you can draw. Whereas, if the object is so big, whereas our drawing sheet is limited, then what we have to do? In the object, if it is say 5 meters, we may have to represent here only the 5 centimeters. That means you have to reduce. That means there should be a ratio between the distance on the sheet to the distance on the object. So, that distance on the sheet to distance on the object, that ratio is called RF. Here it is 1/500 in this example. So, RF is nothing but distance on the sheet or drawing divided by distance on the object. Distance on the object. 1/500 here it is given. So, that ratio, will it be always less than 1? No. It all depends. If it is civil engineering context, all the building drawings, etc., we draw with a reduced scale. You reduce the size so that the RF is less than 1. If it is a compatible size, the same, similar, other, say, certain objects whose size is within the drawing requirements, we will draw it to 1:1 scale. That's called true scale. Whereas, suppose if a wristwatch drawing is to be prepared, okay, then what happens? You cannot see small parts, no? Then you have to expand it. Therefore, in that case, RF will be reversed. 1 by something, no? It is something by 1 like that. So, RF will be more than 1 in that case. In that case, it is called an expanding scale or expanded scale. In the, here, if it is RF is less than 1, it is called a reducing scale. If RF is equal to 1, it is true scale. I have not listed here. In the exam, in the questions, we will discuss all these things. Okay? Okay. So, plane scale, there will be 2 sequential units. That is the importance of the plane scale. Sequential units, one next to the other. For that you need the knowledge of the units. What are the units in our metric system? Meter in the middle if you take, no? Meter in the middle if you take, if you go up 10 meters, 1 decameter, no? 10 meters is 1 decameter. And 100 meters it is 1 hectometer. 1000 meters it is kilometer. If you come down, decimeter, 10 centimeters, 100 centimeters is 1 meter, whereas 10 centimeters is 1 decimeter. That is 1/10 of the meter. 1/10 of the meter is 1 decimeter, and 1/100th of the meter, centi means 100th, no? Centimeter. That means 10 decimeters will make 1 meter, or 1 decimeter is equal to 1/10 of the meter. Similarly, you know this, centimeter is 1/100th of the meter, and millimeter 1/1000th of the meter. So, in the metric system, what is the sequence? Less than meter or decimeter, centimeter, millimeter. More than meter or decameter, hectometer, kilometer. Is it not so? Like that. Now, any side-by-side things, meter and decimeter, these are called sequential units. What are the sequential units for hectometer? More than hectometer, it is kilometer. Less than hectometer is decameter. Like that. What are the sequential units of centimeter? Below centimeter, it is millimeter. Above centimeters is decimeter. So, like that. If there are sequential units, you go with, that is the measure requirement. The measuring requirements involves only sequential units. Then you go for a plane scale. Okay. For example, here you measure in, this scale represents measurement in meters and units are 10 meters, that is decameters. Okay. So 1 decameter is 10 meters, 2 decameters 20 meters, 3 decameters 30 meters, like that. Okay. So how you measure, how you do that? So based on the questions, we'll do some questions, then you will understand that. First of all, plain scale is used for only 1 decimal place for sequential units. If it is less than that, the basic unit we call primary unit, and then the fractional unit we call as secondary unit. Okay. So there will be terms like primary unit, secondary unit. If it is a diagonal scale, we get the third term like fractional unit or tertiary unit. We will see them. Okay. So what is the diagonal scale? In the case of diagonal scale, there also this is common, refractive, representative fraction, or the scale factor is there. Okay. There we construct the plane scale along a line. Just for representing the height, we put this thing. We'll do while doing exam and questions, we'll discuss again. Whereas for a diagonal scale, we develop it on a box, on a rectangle of height some 3 or 4 centimeters. And then the principle is here, if you want third unit, what we do is, we'll get the third unit in a different direction. For example, see, here meters, this is one scale where, say, 0 is here, 1 meter is here, okay, and 2 meters is, like that it goes on in meters. Fraction of a meter, here I will represent. So from here to here also 1 meter, but I divide this into 10 parts. When I divide this into 10 parts, each part become what? 1/10 of a meter, decimeter. Now, if it is a plane scale, I can go only up to decimeters. But if I want to go up to centimeters, that is third unit, third fraction, right, second decimal place, then we require a diagonal scale. If I want centimeters, can I measure between these 2 points 10 parts? Yes. There I cannot measure, but I will expand this in a vertical fashion. That is, you can see here, in an expanded way. What for that we do is, that's why we construct the diagonal scale like a box, Then divide it to the required primary units, and the first unit we require it divide into secondary units. Here primary units are meters, secondary units are decimeters, and fractional units are centimeters. So main scale, in the box, length is divided into required number of primary units. After marking the primary units, you take the first unit, divide it into the number of secondary units. The secondary unit is decimeter. How many decimeter make 1 meter? 10. Therefore, you divide it into 10 parts. 10 parts. Therefore, each part, how you divide? Dividing a line, you know, you take a slant line, divide it with a divider, and connect the ends with parallel lines in between. You can do that. So, you got now decimeters. Now, we want centimeters. For that centimeter, what we do is, we will measure this centimeter, 10 parts of these centimeters, by taking a diagonal line. How? You see, for this distance, this unit vertically if you go, it will be here. So you observe this triangle, you observe. How you got this? We got it. After getting these 10 points, you take from the left side, first point, connect it to the top, and then draw the parallel lines. So here you got 10 points, there also you got 10 points, but the lines are inclined. Now you divide this height into the required fractional unit. What is the fractional unit? Centimeter. Now this secondary unit is decimeter. What is the relationship between deci to centi? 10. Okay. 10 centimeter make 1 decimeter. So because we wanted 10 parts here, you make this height, because I told you diagonal scale is constructed in a box like rectangle shape of height some 3 to 4 centimeters. There is no rule for that. Comfort, that's all. So this height again you divide it into 10 parts. Here I have not shown, it's a small thing. You can, in fact, you can use similar thing by just dividing it into 10 parts by taking the marking there. Or here I have shown you on this side, same thing. We divided. You take a slant line, divide it into 10 parts, connect it to the end and parallel lines, you get these 10 parts. With those 10 parts, draw horizontal lines. With those 10 parts, draw the horizontal lines. Now this is expanded here and shown to you. Now you see, from here to here, this small part is 1/10 of the centimeter. So this 10 steps you go, if you are going those 10 steps from here to here, you cannot measure, but the same 10 steps you are going in this direction, so that separately you can measure. That is through a diagonal. So this is a diagonal scale. That is through diagonal, therefore this is a diagonal scale. So this is how we see, but when you do number of problems, you will understand it better. Okay, so in general I have told you about scales. Now some theory for your examination purpose from wiki I gave you these things. We'll discuss while doing the problems, but there are certain minimum things you have to know. What are those things? I told you RF is one thing. RF is one thing, representative fraction. It's a ratio of distance on the drawing or sheet by distance in the object. And this value RF is maybe, if it is a true scale, it is 1. If it is a reduced scale, less than 1. If it is an expanding scale, more than 1. Okay, so the RF value may be 1 or less than 1 or more than. For all civil engineering purposes, it is always less than 1, because our objects are bigger than the sheet. Whereas for small parts in mechanical or some other nano works like that, we'll expand that. Okay, in such cases only it will be more than 1. Okay, now the simplest scale in 2 units, centimeters, millimeters, or yards and feet, etc., can be a plane scale suitable for number of equal parts and are termed as primary divisions. Suppose, as I told you, sequential units, when you want to measure say meters and decameters, sequential units. So which is bigger one? Decameter is bigger one. So this is primary unit. This is secondary units. Whereas if you want to measure meters and decimeters, which is bigger one? Meter is bigger one. This becomes primary unit, decimeter becomes secondary unit. Similarly, if you want to measure decimeters and centimeters, decimeter becomes the primary unit, centimeter becomes smaller one. Okay, like that. Even if it is other systems like no. In the FPS system, you see feet, yard, inch. Okay, 12 inches make 1 foot and 12 feet make 1 yard. So if you are writing for the 2 sequential units of feet and yards, yards are bigger. That is primary unit. Secondary unit is feet. Each foot is 1 second unit. If you are writing in terms of foot and inches, if you want to measure them using the scale. In that case, the foot is bigger than inch, therefore foot becomes the primary unit and inch becomes the secondary unit. So primary unit, smaller one is secondary unit, still smaller one is, that is what you get in the diagonal scale, fractional unit or tertiary unit. So for the purpose of problems, etc., how you know? I just told you, when you are constructing the scale, I am asking you to divide into numbers, number of parts like that, isn't it so? ఈ నెంబర్ ఆఫ్ పార్ట్స్ కింద మనం ఇవ్వాలి అంటే వాట్ వీ నీడ్, వీ షుడ్ నో ఎన్ని పార్ట్స్ చేయాలి అనేది మనకి తెలియాలి. అది దేన్ని బట్టి ఉంటుంది అంటే ప్రాబ్లం ఇచ్చిన దాన్ని బట్టి ఉంటుంది. మనకి ఇచ్చినటువంటి ప్రాబ్లంని బట్టి మనం అది డిసైడ్ చేస్తాము. లెక్కలు చేస్తున్నప్పుడు అది తెలుస్తుంది. దానికే ఇక్కడ ఫార్ములాలు ఇచ్చామన్నమాట. N1, వాట్ ఈజ్ N1? నెంబర్ ఆఫ్ ప్రైమరీ డివిజన్స్. ఒక స్కేల్ తీసుకున్నాక ఫస్ట్ దాన్ని ఎన్ని డివైడ్ చేసాం అన్నది ప్రైమరీ యూనిట్స్. 1 minute. Okay, so like that we will see that. 1 minute. 8:30 daaka. Okay, so tomorrow onwards we can. Okay, so today we have to close by 8 o'clock. I said today I will take up to 8:30, but from tomorrow we will try that because of some problem. Okay, anyway, so we will continue this. Next we will have discussions on how to draw the scales. With some examples we go, and then the explanation I already told you this. Then we will have practical observation with certain data. Okay, you can do that. Similarly, some more details about the scales we will see, and then some questions we have to. So all these were ready, but because of today's time constraint, I am stopping it. Thank you. What we have discussed today is beginning from the polygon properties, geometric figures, etc. Then we went for fundamentals of orthographic projections, wherein we discussed picture planes, etc. And then other things like scales introduction we did it. Thank you.